Alright, so let's look at the last section of this chapter, which is on function composition and inverses. Okay, so first we're going to start with the definition of the equality of functions. So if we let f and g be functions from set A to set B, then f is equal to g if and only if f of x equals g of x for all x in A, in the domain. Two functions that have different domains cannot equal. So that's a condition for two functions to be equal, is that they do start with the same domain. Alright, so let's look at this example. Alright, so are the following functions equal? So we have in part A, we have the function defined on the integers. So integer to integer, where f of x is x squared. And we have a function g, which is defined on the real numbers, where g of x equals x squared. So we notice that the equations are the same, the formulas are the same, but the domain of f is different than the domain of g, so the functions will not be equal. Alright, so if we have domain of f is not the same as the domain of g. So f of x is not equal to g of x. Okay? So if you think of the graphs of these functions, it should make sense why they are not equal to each other, right? So let's see if I'm going to graph f and g. So here's my x and here's my y. Let's do 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. Right. Okay. So let's graph f. So f is, the inputs are integers only and you square them, right? So if I put in 0, I'm going to get 0. If I put 1, I'm going to get 1. If I put 2, I'm going to get 4. Right? If I put -1, I get 1. If I put -2, I get 4. Okay, and so on, right? Right. But these you cannot connect with curves because your inputs are just integers. So your f function is just the dots. Right? Now, if I graph g is x squared over the real numbers, I would still pick the same values to draw, but I would be able to connect it with curves because all the other values in between are part of my domain. So this is the g function. Now the red is not the same as the blue. Okay, so because they don't have the same domain, so just the dot function is not equal to the full curve. So they're not equal to each other. Alright, so now let's look at part B. So part B, I have two functions, h and k, which are defined as follows. Okay, so let's see. H has domain -1, 0, 1, 2, and range 0, 1, 2, or codomain 0, 1, 2. And h is defined as the absolute value of x. And the k has the same domain and codomain. And k is defined as follows. Okay, so let's see if these are the same. Now they don't look like they're the same if you just look at them. But because we have just a few values in our domain, we can evaluate and see. So let's take our -1, 0, 1, 2. They have the same domain, so that's a check. Right? So let's figure out what h is. So h of x is absolute value of x. So if I plug in the values in my domain, I'm going to get 1, 0, 1, 2. Okay. Now let's evaluate the k function. The k function is given by -x cubed over 3 plus x squared plus x over 3. Alright, so let's see what happens if I plug in -1. Right, if I plug in -1, I'm going to get a positive 1/3 plus 1 minus 1/3, and this gives me 1. Right? If I plug 0, I get 0. If I plug 1, I get -1/3 plus 1 plus 1/3, which is also 1. If I plug in 2, I'm going to get -8/3 plus 4 plus 2/3. So I have 12, 14 minus 8 is going to be 6 over 3, which is 2. Okay, so for these values in the domain, the output values of the two functions match. Now, they might not match for other values. If I plug in -2 or 4 or 10, they probably will not be the same. But for those few points, which are, it's the whole function because that's the domain that we're taking, these functions are equal. H of x is equal to k of x over that domain that's given. Okay? Now we can do operations on functions. Again, this is familiar from algebra. I can add and multiply functions together. So if I have functions a, g, both go from the same domain to the same codomain, then the addition and multiplication of those functions are also functions from a to b for all the values of x in a, and they're defined by this. We add the functions and we multiply the functions. Okay? So let's have f and g be functions from the real numbers to the real numbers. So f is x squared and g is x minus x squared for the function f plus g and f times g. So the function f plus g is just the x plus x minus x squared, which gives me x. And the multiplication fg is going to be x squared, x minus x squared, which gives me x cubed minus x to the 4. Alright. Now let's define another operation between functions called the composition of functions. So f is a function from a to b, and g is a function from b to c. And this is important. So to compose two functions, the codomain of the first function has to be equal to the domain of the second one. So the composition of f followed by g is written g of f. Notice the reverse of order. So it's a function from a to c defined by g of f of x, which is g of f of x. Okay, so basically plugging the f function into the g function. So the order goes that we have f followed by g means I'm going to take an input from a, apply the f function, and this is my output. And that output is going to be used as the input for g, and you apply the g function to get another output. So the composition goes directly from set A to set G using a combined or composed rule, right? So let's look at example 3. So f is from set 1 to 3 to set AB, and defined as follows. G is from set AB, good, can these match, to set 5, 6, 7, and those are the rules. Find g of f and f of g. Okay, so g of f, this composition means g of f of x. So it means that you start with applying the f function first. So you're going to get the domain of the f function 1, 2, 3 mapped into AB. And so if I apply the f function here, f1 goes to A, f2 goes to A, and f3 goes to B. Okay, so that's the action of the f function. Now the g function, because the g function starts at A, so they can start with the same outputs and go to number 5, 6, 7. Right, so let's apply the g function. So the g function says that A goes to 5 and B goes to 7. Okay, so when I compose it, g of f of x, right, says that if I start with the input of 1 right here, then that's going to end up with the output of 5. Right? And if I start with the input of 2, this will also end up with an output of 5. And if I start with an input of 3, this will end up as an output of 7. Okay, so those are the rule that shows the composition with these inputs and those outputs. Okay, now let's look at part B. The part B says find f of g of x. Right? So f of g of x. Okay, so my inputs for the g functions are, the domain are a and b, and my outputs are 5, 6, 7. Okay? Right, but notice that there's a problem here, because these outputs right here need to become the inputs for the f function, but that doesn't match because the inputs for the f function are 1, 2, 3, not 5, 6, 7. Okay, so because the codomain of the g function is not the same as the domain of the f function, this composition cannot be done. So this is not possible. Okay, so I can find it one way. I can find the g of f of x, but I can't find the f of g of x. Right, so let's look at an example of composition with formulas, with equations, rather than with the arrow diagrams or the sort of point definition. This is what we're most familiar with from algebra. So let's say f is x cubed and g is 3x plus 1. They're both going from the real numbers into the real numbers. So the codomain of one is going to match the domain of the other and vice versa. So we can do both compositions. Okay? So g of f of x means that we are plugging f into the g function. So the g function is 3x plus 1, but x gets replaced by the f function. So we just get 3x cubed plus 1. Right? And the f of g function, we have f of g of x. G gets input into the f function. So my f function is x cubed. So when I replace x by the g function, I get 3x plus 1 cubed. And I'm not going to expand that out. Let's look at one more. So let's have g be the function from set ABC to itself with that rule. And f is from the set ABC to 1, 2, 3 with that rule. And let's find a composition of f followed by g. So we're going to do g of f, which is g of f of x. Okay. Well, see if they work, and if they work, then we do them. So g of f of x, we're starting with the inputs for the f function. So the f function goes from a, b, c onto 1, 2, 3. Okay, so this is for the f function. Now the g function goes from a, b, c into itself. Okay, so this is not possible. Okay, so it's not possible to do this because the output of the f function is different than the input of the g function. Okay, so this one is not possible. So let's look at the other way. G followed by f, so we're doing f of g of x. Okay. And this one starts with ABC is the input, or the input values, going into ABC. So we're going to do the g function first. Okay. And these outputs need to be the inputs of f, and that will work because the inputs of f are ABC, and we want the outputs to be 1, 2, 3 for the f function. Alright, good. So we know that composition is going to work that way. Okay? So let's see, for the g function, a goes to b, b goes to c, and c goes to a. Okay? And for the f function, a goes to 3, and b goes to 2, and c goes to 1. Okay? So I can write f of g of a, so starting with this, this is going to end up at 2. F of g of b, this is going to end up at 1. And f of g of c, this is going to end up at 3. Okay, so this is the values of the f of g composition. Okay, so we're going to mention some properties of function composition. I'm not going to prove them. We're just sort of, it's interesting to kind of see the properties, and those are used fairly intuitively without thinking much about them. So first one, function composition is associative. So if f goes from a to b, g goes from b to c, and h goes from c to d, then I can do this, the function compositions. I could either do g composed with f first and then with h, or I could do h composed with g first and then with f. Now you can't switch the orders. Like you couldn't switch f with h or g with h because these need to match. Like these output input need to match, and these output input need to match. So it has to be in the order h, g, and f, but it doesn't matter which ones you do first in that order. Right. Next definition, powers of a function. So if I have a function on a set A, so it goes input and output are the same set, then you can define powers of functions to be function composed with itself. Okay, so f1 means the function itself, but the other powers means like f squared means f of x, fn means f of x n times, right? And you say f and n plus 1 is the function composed of f of n, right? Next property, the composition of injections is an injection itself. So if you compose two functions that are 1 to 1, then the composite function will also be 1 to 1. And same goes for onto. The composition of surjections is a surjection. So if you start with two functions that are onto, then the composition is also onto.